Now, our first presentation is going to be on predictable vFabric on informative data plane, and the presentation will be given by Chuang Wang, and this will be one of the online presentations, the recorded ones. And the reason is that the student really wanted the opportunity to give the talk. Nevertheless, the advisor is here to be able to answer questions afterwards. Chuang Wang is an assistant researcher at Chongrong Laboratory, and he got his PhD from Tsinghua University in 2022, advised by Professor Dan Li. This work was done when he was an intern at Alibaba Cloud. He's broadly interested in computer networking with a special focus on high-performance data center networking. So, please play the presentation.
Hello everyone, I'm Shuai Wang from Tsinghua University, and in this talk, I'm going to present our work on how to build a predictable virtual fabric in multi-tenant data centers. This is a joint work with our collaborators from Alibaba Cloud, Zhongguancun Laboratory, and the University of Cambridge. For the next generation of data center network, applications are expecting very predictable network performance. Many factors drive this trend. First, in high-performance storage, faster and faster storage devices are shifting performance bottleneck to network because we want to support millions of LPS and tens of microsecond latency. Second, in distributed machine learning, the dedicated training clusters uses thousands of accelerators to speed up training. Model parameter synchronization among these accelerators consumes lots of bandwidth and requires a response time of no more than 1 millisecond. Third, in recent years, resource disaggregation is accessing remote memory through the network, so it is very time critical. So we can see that today applications are becoming increasingly sensitive to data center network performance anomaly at microsecond granularity. We studied the performance of existing practices in Alibaba Cloud, including both production compute and storage scenarios, and the observation is consistent. So DCN capacity is largely over-provisioned. It still cannot efficiently isolate network resources among tenants at short-term scale. We can see that the burst traffic from another tenant can cause 50 times latency inflation. On the other hand, modern DCN has rich paths and uses ECMP to split traffic among different paths. However, it is not non-trivial to aggregate multiple parallel paths as an ideal pipe. We take an aggregation switch to monitor its uplink load and observe that harsh polarization and elephant flow can easily cause load imbalance. This issue comes from today's best effort network service. Today, data center network has no guarantee on bandwidth and latency, so the application has to be deployed in different clusters to avoid bandwidth contention. To improve latency, tenants prefer to use advanced congestion control in their applications. However, the co-design of network and applications for providing guarantee on bandwidth and latency involves both network operators and tenants, which needs huge efforts but got limited gains. Today's DCN only does its best to transmit packets, so the quality of network service is not guaranteed. The next generation of DCN should provide a predictable network service for applications, so tenants can enjoy the guaranteed bandwidth and the latency, simplifying the application design. Also, DCN operators can benefit from the predictable network service due to the performance improvement of the shared cloud. In this work, our goal is to provide a predictable DCN service for multiple tenant data centers. We use the host model to abstract the tenants' virtual fabric. Each group of VMs can view their own network as if they are in a dedicated fabric. So these tenants share the same physical network infrastructure. Specifically, a predictable worker fabric should provide bandwidth guarantee. That is, the guaranteed bandwidth can be quickly provisioned if the tenant has sufficient traffic demand. And it also can achieve network observation. A tenant can use more than its bandwidth guarantee to fully utilize the network resources if other tenants do not have sufficient traffic demands. Finally, it can bond the end-to-end tail latency. For predictable DCN service, all three goals should be achieved simultaneously. Lots of efforts have been paid in this area. Some work uses static bandwidth reservation to provide strong guarantees, but achieves low resource utilization. There are traffic admission control as the end host to provide bandwidth guarantee at edges, but they assume a congestion-free fabric, which is invisible in reality. The last piece is weighted congestion control. They can achieve weighted fabric bandwidth allocation in runtime, but can work slowly. Since no single work can provide the above three goals simultaneously, we use Picnic, weighted congestion control, and Claw for the state-of-the-art performance. We take an in-cast example to show that it is not easy for the PWC combination to achieve latency guarantees. Existing congestion control heuristically involve flow rate to achieve full network utilization. So more active flows in the network would exaggerate the upper bound of the burst and finally lead to unbounded queue latency. In contrast, MuFab can bound the tail latency even as the in-cast degree increases. As another example, we have three virtual fabric going from the cluster in the left to the cluster in the right. Then another virtual fabric enters. With the PWC combination, the sending rate fluctuates and the bandwidth guarantee is broken. Because link utilization misleads VF4 to perceive the essential bandwidth contention. So we can say that bandwidth isolation in multipath architectures is not orthogonal to load balancing, and they must be considered as a whole. With this principle in mind, MuFab can converge to the expected bandwidth allocation when VF4 enters. The insight here is that the traditional DCN fabric is a black box for the end hosts. So end hosts do not know what is going on in network fabric, and they typically use a heuristic for the rate adjustment and path selection. As a result, it takes a long time to perceive the path quality and convert to the demanded bandwidth. In recent years, programmable network devices are deployed in data centers, and they bring possibilities to obtain real-time and precise network information. With this information, senders can adjust the rate and select paths more accurately and rapidly. That opens up new opportunities for the senders to perceive the path quality and convert to the demanded bandwidth in sub-millisecond. This is the architecture of MuFab. Each host has an active edge, MuFab E, and the switches are the informative core, MuFab C. When the sender sends traffic to the receiver, it generates proper packets and sends them to a network. Every time the proper packets reach a switch, the switch will insert virtual fabric information into proper packets, including not only network information, but also tenant information, such as the link capacity, link utilization, bandwidth guarantee, and etc. The tenant information enables MuFab to perform tenant-level network isolation. In this way, when the proper packets reach the receiver, all necessary information will be collected in the proper packets, and then will be picked back to the sender. Based on the feedback, the sender can schedule packets to different paths and control sending rate of each path. So how MuFab achieve bandwidth guarantee with work conservation? With the VM pairs token and the link capacity recorded in the switches, different VM pairs can use proportional sharing to allocate bandwidth. because proportional sharing based on VM pairs guarantee provide a very quick judgment about the overall bandwidth guarantee. That is, either every VM pairs bandwidth can be guaranteed or none of them can be guaranteed. But what if some senders do not have sufficient traffic demand? To solve this problem, we also record the switches output rate and the VM pairs sending rates. If some senders have insufficient traffic, total text rate will be less than the link capacity and lead to the increases of the expected sending rate. We use uppercase R as the expected rate and lowercase r as the lower bound, and allow the expected rate to go beyond the lower bound. Further, we use window-based traffic admission to limit the in-flight traffic. By taking Q-length in switch port into consideration, we can handle short-term traffic bursts efficiently. But there is another problem. When the link keeps being underutilized, all VM pairs can grow to a full line rate, even they have only one token. Then, if multiple VM pairs have traffic demand simultaneously, total in-flight traffic and worst cases latency are still unbounded. To solve this problem, we limit the initial burst of each host to its bandwidth guarantee, and then make them slowly convert to the work conservation. The intuition behind this is that the tenant pays for its guarantee, but the extra capacity is a bonus. In this way, we can limit the maximum in-flight bias to 3 times BDP. When the bandwidth guarantee cannot be satisfied, we should migrate the VM pair to another path. We do this quickly but with caution. Besides, if there are more bandwidth in other paths, it is better to migrate to other paths to achieve work conservation. But we can do this less frequently. The insights are that with the precise information from the network, we do not need to actually put the traffic into the path before we can do the migration. And randomization and pacing techniques are used to avoid occlusion and reordering. We implement MuFab-E prototype in both FPGA-unique and SoC-unique to understand the complexity and the real application level performance. The implementation in FPGA consumes only 10% extra bandwidth resource. The MuFab-C prototype is implemented in Tofino. The switch maintains the sum of the bandwidth tokens and the new window for the active VM pairs, which is tracked by a Bloom filter. This is our test bed. We generate traffic from the left port to the right port with 3 kinds of bandwidth guarantees. MuFab converges to the bandwidth guarantee quickly and steady. However, the PWC combination causes rate fluctuation and cannot satisfy the bandwidth guarantee. Besides, MuFab can achieve close to 0 Q-length. With the FPGA test bed result, we can see that MuFab can convert to the bandwidth guarantee very quickly, even with a failure. Also, the Q-length is very short and no more than 3 times BDP. We run bandwidth-hungry MongoDB application and latency-sensitive memcached applications simultaneously. In both scenarios, MuFab can achieve close to ideal performance in query per second and query completion time because it can provide predictable network services for both MongoDB and memcached. For elastic block storage application, we also find the similar observation. To conclude, in the next generation of data center, the applications demand predictable network performance and microsecond granularity. We have 2 takeaways. First, the network should provide their predictable services to applications, and this service has to be built in the fabric layer, so we can avoid the invisible VM modification. Second, edge core fusion with programmable data plane can help to get fine-grained network information and get the senders to make smarter decisions. Together, this is the MuFab, which provides bandwidth guarantee, work conservation, and bonded tail latency simultaneously. That's all. Thanks. We will take the following questions.
Thank you very much. And we have one of the authors here to answer questions. So please, come up.
Oh, okay. Jun Kim from Princeton, great talk. I guess my question was, do you need this vFab stuff? So do you need all the servers to have the smart NICs and also the programmable data planes in the data center, or can it be partially deployed and it still works?
So you mean that the deployment can be like incremental, or do you need the full deployment, all the switches need to support, and all the hardware need to support? From our current evaluation, we assume that all the smart NIC and the switches can support all the functions. Okay. Maybe we can think about in the future for the incremental deployment.
Okay.
Hi, Simon Wass from Intel. Thanks for a great talk. If you have a link that's already near capacity and you have two VM pairs that decide to start sending flows at the same time and choose the same path, where the window allocation system indicates that there would be room for one to add its bandwidth, but two happen to start at the same time, what will the system do in that situation? Will they both try and migrate at the same time, like immediately?
So you mean, in cast scenario, two senders send traffic together at the same time? So in this case, the key idea for microfabrics, we want to have a utilization convergence together with fairness convergence. So when everyone sends the traffic the first time, they will announce their weight, which is the switch maintains subscription. So they know that all the weight from all the vendors. If in the first round trip time, everyone send the traffic, the two guys send the traffic simultaneously in an in-cast scenario, it will cause the burst, right? So, but we control the initial window, so make sure that everyone will satisfy their minimum bandwidth guarantee. So there's no bandwidth, they will not hurt bandwidth. And in the second round trip time, each one will know that another flow or another VM is competing the link, so they can fall back.
Okay, thank you very much.
Sure.
Any additional question? If not, I have one, and that is, what is the time scale at which you would migrate? Would you migrate every millisecond, every 100 milliseconds? What are the time scales for the various different steps of your architecture?
So what's the time scale for the flow convergence or for the bandwidth negotiation?
For the bandwidth migration, so you had multiple different steps in which you are changing paths, in which you are readjusting your architecture, etc. So what are the time scales for these?
We have two strategies, as we mentioned. If one path cannot guarantee their bandwidth, they have to switch path immediately, because that's the violate the SLA. And in the second scenario, is when one virtual machine wants to increase their bandwidth for work conserving. So in this case, we do it less frequently. We typically is once every couple of millisecond level for the second case.
Thank you. There's one more question.
Yeah, in continues to your question. So you're saying you're changing immediately the path, but how you resolve out of order that you're now creating due to the new path that you're now giving the ability to move more traffic, and probably it will bypass the traffic that you send on the older one. So how do you cope with the out of order that you create? It can make, you will probably need a very large out of order buffer, reordering buffer.
So you want to, the question is how to avoid out of order and those kind of stuff, right?
Yeah, if you're changing the path immediately, as you answered right now, you will cause out of order. And it can cause a big magnitude, because if, for example, you only satisfy 20% of the SLA, now you gave me 80% of the SLA in a much faster path, then the out of order degree will be very large.
Okay, so first of all, if the path cannot satisfy the SLA, we have to change it anyway, even though you have an out of order issue That's the first point. And the second point is we have a strategy to avoid out-of-order issue necessarily. For example, we have a probing packet every round trip time, so they will know that once we receive the probing response, we know the previous window has been successfully delivered. In this case, we can switch paths very, very safely. So we do that? Okay. Yeah, we have a self-clocking to avoid out-of-order issue.